Okay, we're all set and ready to get started. So we're going to be talking through this practice exam for exam 1 for Chem 101. So any questions before we get started? Okay, so let's start by talking about the first question. So this is very similar to note set 1. We're asked to classify the following as physical or chemical changes. Okay, so let's just read through each of these statements and assess that. So metals dissolve in acidic solution, yielding hydrogen gas as a byproduct. So we see the words product and yielding. What does that suggest? What does that suggest? Chemical. Yep, this suggests a chemical reaction taking place. So benzoic acid readily dissolves in solutions of acetic acid. So the dissolves keyword, solubility, is that a physical or chemical property? Physical. When things dissolve, it's a physical change. And solubility is a physical property. Nickel tetracarbonyl readily sublimes. So subliming is going from the solid state to the gaseous state. So phase changes, are those physical or chemical changes? Physical. Yep. Perfect. Any questions on this set? Again, the key criteria between physical and chemical changes is that for physical changes, the chemical formula, the chemical composition of matter does not change. Only the state. Yes. Oh, okay. So let's talk a little bit and classify the following as physical or chemical properties. Again, our criteria when we're assessing physical or chemical properties, does our chemical formula change? So alkaline earth metals react with water to generate basic solutions containing metal hydroxides. Well, there's one word that is a giant signpost here. The word react. What does that suggest? Chemical. Yep. Argon gas is more dense, so circling that. Density, can we observe density without changing the chemical composition? Yes, so what kind of property is that? Physical. Yep, perfect. Okay, let's classify the following as a homogeneous, heterogeneous mixture or a pure substance. So carbon monoxide. So carbon monoxide is a compound, right? So elements and compounds are considered what? Pure substances. So this is a pure substance. Likewise, looking at HCl gas. So hydrogen chloride. Is there anything else mixed in with this hydrogen chloride? No. So is it a pure compound? Is it a pure substance? Yes. Okay, perfect. Any questions on these?
So,
yes.
why then why is it again a pure substance?
Which one?
For C.
For, okay, HCl. So pure hydrochloric acid exists as a gas. There's no other pure substance mixed in with that hydrogen chloride. Just as a side note, if you happen to see, for example, HCl aqueous, this aqueous would imply that it's dissolved in water. And this, anytime you see the aqueous symbol, that's a clear signpost that you're dealing with a homogeneous mixture. Because the aqueous is implying that it's dissolved in water. Yes.
So here we just have to memorize HCl gas. It's one thing because I thought I mixed
it is a single compound and a single pure substance. Does that make sense?
Yeah.
In order for something to classify as a mixture, there must be more than one pure substance combined together. So 2 or more pure substances combined together.
Okay, so then we just have to memorize that HCl is a pure substance.
Well, the other way to think about it is anytime your state symbol, anytime you see only one compound or element, and the state symbol is not aqueous, implying it's dissolved in water, then it's going to be a pure element or compound, and as such, it would be a pure substance.
Okay, that makes sense.
Mhm. Any other questions on this? Yes. Heterogeneous. So you, for example, the best example of a heterogeneous mixture would be oil plus water. So you have two or more pure substances that do not mix. So there is a clear phase boundary. Inconsistent composition throughout. Those are the keywords you should look at when you think about heterogeneous mixtures. Okay, let's keep moving on. Any other questions? Okay. So in the next set, we're asked to classify the following as a compound, element, or mixture. So sulfuric acid, which is H2SO4. Do we see more than one element? Yes. So a species containing two or more elements would be called what? Compound. Yep. Okay. Ozone, O3. Do we see two or more different elements? No. So what is ozone? Element. It's an allotrope of oxygen, and it would best be classified as an element. Any other questions? Yes. Would be a mixture. So for example, nitrogen and oxygen, air, these would be examples of mixtures. Or H2O, so just pure water. Are there two or more pure substances? No. So the H2O would be a compound. Does that make sense? Perfect. Okay, so let's take a look at the following table, and we're really going to need our periodic table for this one. So let's zoom in on the relevant region of our periodic table, and allow me to erase a little bit of the components that we've included from our previous lecture so we can have a little bit more clarity in this discussion. Okay, perfect. So now let's go back to our practice exam and let's take a look at what's being asked. So we're given the name for bromine. So first things first, the element symbol is a freebie. So let's go to our periodic table. And would someone like to volunteer? What is the element symbol for bromine? Br. Yep, perfect. And while we're here, any other information? We'll go back to that in a moment. Okay, so bromine is Br. Okay. What is the common chemical formula? And for this, let's really start to think about the group name and group number, as that gives us some insight into the chemical formula. What's the group number or group name for species such as bromine? 7A, but I'd like you to provide me the halogen name. Because I said, tell me the group name or the group number if there's no common name. So these are the halogens. The reason why this is important, the reason why I asked you to think about this is because halogens in general, are they monoatomic, diatomic, or polyatomic? Diatomic. So the chemical formula would be Br2. Yep. This is one thing that you will have to look through your book and devote to memory, as it's something that I'm especially interested in, and it's necessary for later chapters in describing chemical reactions. The state of bromine at room temperature is a liquid. And that's found in your textbook in chapters, I believe, chapter 3. Yes?
Would we get marked down if we just put halogen instead of?
Oh, yeah, halogen would receive full points. 7A, you'd get a slight markdown because I wanted the group name. Is bromine a metal, non-metal, or metalloid, or a noble gas? Non-metal, yeah. Yes.
So on the halogen,
Yes.
in that column, all of them will be the 2.
Yes, so looking at the periodic table, all of our halogens are diatomic. They have the form X2. Yep. Now, looking at the current periodic table that we have, the periodic table is a little bit mean, the one that I've given you. The one on the exam is a little bit nicer. So let's use the one on the exam, actually, just to make things easier. So let's go up to our periodic table on the exam. And so so we already established the group number is 7A. What do we call the period number? What does the period number represent? So if groups are columns, periods represent rows. So we have 1, 2, 3, 4, 5, 6, 7. So what row is bromine found? 4. Yep. So we have a period number of 4. Perfect. So let's go and fill that in. So our period number is 4. Taking a look at the periodic table once again, reading off from the periodic table, what is the atomic number of bromine? So 35. So let's just showcase that. If we go right above bromine, we see the atomic number above the element symbol, which is 35. Wonderful. Okay, perfect. So we've completely filled in the table for bromine. Let's now move on to our next element. So we know that it's an alkali metal and it has a period number 3. What group number are the alkali metals? Not alkaline, but alkali. 1A. Yep. Okay. So now we're ready to go to our periodic table. So we're looking for column 1A, and then our period number, which is our row number, is 3. So what element corresponds to that? Sodium. Okay, perfect. So then the element symbol is Na, and we'd call this sodium. What's the physical state of most metals at room temp? Solid. Yep. And are most metals monoatomic, diatomic, or polyatomic? Mono. Yep. So the formula would just be Na. Is sodium a metal, nonmetal, metalloid, or noble gas? Metal. Yep. It's your stereotypical metal. And what is the atomic number? What number appears above sodium symbol? 11. Just to showcase that once again, if we go to sodium, the number above sodium symbol is 11, right? Okay, perfect. So we finished that entry. This one, we don't have a lot of information, but we actually have the most critical piece of information needed to identify an element. We have the atomic number of 9. So then let's take a foray into our periodic table once again. And let's see, where do we see an atomic number of 9? Fluorine, yep. Here we go. And while we're here, do we know the group number and the period number? Yeah, so let's read those out once we're back in our table. So we've established that this element is fluorine, F, fluorine. Before we fill out the state at room temp, what is fluorine's group name or number? Halogen. It's 7A and it's a halogen. Now this is important because does that give us insight into the chemical formula? What is the formula of fluorine? F2. Additionally, do we know the period number of fluorine? 2. Yep, we can just read that off from the periodic table. Is fluorine a metal or non-metal? Non-metal, yep. And what's the physical state of fluorine? It's a gas. In general, your non-metals that are high up on the periodic table and far to the right are going to be gases. Okay, mercury, quite an infamous element. What is the symbol for mercury? Hg, yep. And we've all seen a mercury thermometer. What's the physical state of mercury? Liquid, yep. Now, going to the periodic table, let's now go and find mercury. So we went and we found, where is it? Hg, all the way down here. Do we have the group number and the period number? Yes, okay. Our group number is going to be 2B. Our period number is 6. Any other information that we need? Do we have the atomic number? 80. Yep, we can read the atomic number off from this symbol as well. Okay, let's now fill in our information. Let's fill in our information into this table. So it'd be Hg, as most metals are monoatomic. Mercury is in fact a metal. What's our period number? 6, yep. And what's our atomic number? 80. Is there any special group name for 2B? You can technically call it a transition metal, though that's not specific for a given group. I wouldn't fault you if you included that as extra information. Transition metals refer to the set of groups in the middle of our periodic table. Okay, let's switch colors once again and let's keep going through this. So now He, what's the name of He? Helium, yep. Okay, before we talk about the formulas and physical states, looking at helium in the periodic table, I'm going to go to the periodic table right now and let's find helium. So we found He, helium. What group? Noble gas. 8As are our noble gases. And that's really important because if we can identify the group identity, since helium is a noble gas, what is the physical state of helium at room temperature? Gas. And are noble gases monoatomic, diatomic, or polyatomic? Mono, right? So they would just be He. And we've already established that helium is a noble gas. It's also technically a non-metal as well. Just to help me out here, what is the period number for helium? 1, yep. And what is the atomic number? 2. Okay, perfect. Any questions so far? Okay, we're now given the period number and the atomic number. That's a bit overkill. That's too much information, actually. You have excess. Let's now go to the periodic table and let's find the period number and the atomic number. So atomic number of 4, period number of 2, that corresponds to what element? Be? Beryllium, yep. While we're here, 2A, does that have a special name? Group 2A. Alkaline earth metals. Okay, perfect, perfect. So let's fill that in. Let's fill that information in. So we've established it's Be, beryllium. Is beryllium a metal or non-metal? Metal. Why is it a metal? What side of the periodic table is on? On the left, exactly. So are metals typically solids at room temp? Yep, so we'd say solid, that's pretty reasonable. And are metals monoatomic, diatomic, or polyatomic? Mono, right? So it'd just be Be. And as we've established, beryllium is an alkaline earth metal. Perfect. Okay, remember how in class we discussed the periodic table is arranged in order of patterns of repeating reactivity. So if we have the same group number, does that tell us something about the elements having similar or different properties? Similar. So then what 2 elements in this table have the same group number and similar properties? Bromine and fluorine, right? Are these both noble gases? Sorry. Are these both halogens? Yes. Sorry about that. That's a slip. One of the previous exams, I had 2 noble gases. So these are both halogens. They're in the same group, and as a result, we'd expect fluorine and bromine to have similar chemical and physical properties. Okay, let's keep going. Let's keep going. So next we're asked to complete a table using isotope notation. So I'm just going to fill in a cheat sheet above the table. So the number of protons is equal to our atomic number, which we can get from the periodic table. The number of neutrons is equal to our mass number minus the number of protons. And our number of electrons is equal to our number of protons minus the charge. These are just formulas that we've discussed previously in the note set on isotope notation. Okay, everyone comfortable so far? So now let's take a look at fluorine. What is fluorine's atomic number? So if we go to the periodic table, I'll do this by tabbing just to make things easier so it's not so much of a disorienting factor. So if we look at fluorine, what is the atomic number of fluorine? 9. Perfect. Okay, so we can go to, we know the atomic number is 9, so we have 9 protons. So for our number of neutrons, let's change our pen color. Do we know the mass number from this symbol? Yes, so this number in the upper left-hand corner is the mass number. So we have a mass number of 19. We have 9 protons. That gives us a total of 10 neutrons. Does that make sense? Finally, let's figure out the number of electrons. So the number of electrons is the number of protons, which is 9 minus the charge. Is there any number specified for the charge for this species? So that's based on periodic terms, but in this current symbol, are there any charge symbols? No. So we're just looking at the neutral species for now. So we just subtract 0. The -1 is the general trend for ionization, but when you're looking at these sort of problems, you just read off the symbol exactly as written.
So we're just reading it out exactly as it is,
Yes. Mm-hmm.
not the general one?
You're not predicting the charge of the preferred ion. You're just looking at that specific isotopic symbol and counting the number of protons, neutrons, and electrons.
Okay, so if there's no charge, we just assume a 0.
Yes, for isotope notation questions. Okay, let's now repeat this exact same process. Now let's look at arsenic, As. Okay, let's go to our periodic table and let's find arsenic. It's a relative of phosphorus. What is arsenic's atomic number? 33. Perfect. So then let's go to fill in. We have 33 protons to work with. Again, do we know the mass number for this species? Yes, so we're going to take 75 minus 33. My apologies, but my calculator is not visible in the document cam today, but if you punch that into your calculator, you should end up with 42 neutrons. Did everyone get that? Okay. Let's now move on and let's count the number of electrons. It's the number of protons minus the charge. How many protons do we have? 33. And then what is, oh, oops, one moment. And then what is our charge? What is our charge? Yep, so when we're subtracting a negative, that's the same as addition. So it's 33 plus 3. That gives us 36 electrons to work with. Anions in general, do they have more electrons or less electrons than protons? More. Anions have more electrons than usual. Does that make sense? Okay. In this case, you're given all of this information, and now you're going to have to assemble the mass number, charge, and atomic number scheme. So for this specific type of problem, we're going to have to take a slightly different approach. So first and foremost, we know our number of neutrons and our number of protons. So given that we know the number of protons, can we figure out what element this is? Yep. Yep, exactly right. It's boron. So if we go to the periodic table, we find an element with atomic number 5. Lo and behold, that in fact is boron. Wonderful. So now we can go and we know that we have boron. If we wanted to figure out our mass number, we take our number of protons and add up our number of neutrons, and that gives us a mass number of 11. Does everyone understand where we got that number from? The mass number is the number of protons plus the number of neutrons. Next thing we're going to do is we're going to calculate the charge. So the charge in this case, so if we were rewriting an expression for charge, so charge in this case is equal to our number of protons minus our number of electrons. And filling in here, we have 5 protons, and how many electrons do we have? 2. So then that gives us positive 3. So we have a charge of positive 3. Okay, so we filled in all the information as required in this problem. Any questions? Okay, let's keep going then. So we're back to more isotope notation dissection. So going to zinc, if we look up zinc in the periodic table, what atomic number do we have for zinc? 30, perfect. So we go to our entry sheet and we punch in 30. Next, let's figure out the number of neutrons. So the number of neutrons is equal to our mass number. Do we know our mass number? Yep, 64 minus our number of protons, which is 30. That gives us 34. Let's now figure out our number of electrons. So our number of electrons is our number of protons minus the charge. And what is our charge in this case? Yep, so plus 2. 30 minus 2 gives us 28. Did that make sense to everyone? Okay. Any other questions? Okay. If not, we'll continue on. So let's talk next about, so we're asked to assume this ion has a +1 charge. Okay. So we have something X with a +1 charge. Okay, so if we have 54 electrons, how many protons would we need to have a +1 charge? Yep, exactly right. So we'd have to have 55 protons. So to make this a little bit more explicit, the number of protons is equal to the charge plus the number of electrons. So in this case, we'd have 1 plus 54 gives us 55. So that's how we got 55 protons from. Now from this information, can we identify the element? Yes. Okay, so let's go to our periodic table. What element has an atomic number of 55? And I'll have to zoom in over here. Cesium. Perfect. So now let's go back to our exam. So this is cesium. It has a +1 charge. We've established that already. And if we want to calculate the mass number, can we add up our protons and neutrons to get the mass number? Yeah. So 55 plus 82 gives us 137. There we go. Short, sweet, and to the point. Any other questions on this? Let's do one more as required by this exam. Okay, so in this case, we're asked to assume that this is an ion with a -1 charge. So we have 36 electrons. So our number of protons is equal to our charge, which is -1, plus our number of electrons, which is, yep, 36. 36 minus 1 gives us 35. So we have 35 protons to work with. Can we go and find that element in our periodic table? Yeah, so let's do just that. So we go to our periodic table, we go to find an element with atomic number 35, and lo and behold, what element is that? Bromine. Perfect. So bromine is showing up again, except this isn't quite bromine, this is bromide, which is bromine anion, just to be 100% accurate. And now when we're calculating our mass number, can we add up our protons and neutrons? Yeah, so we'll take 35 plus 44, that gives us 79. Perfect, so this table's all filled in. Any questions on isotope notation? Okay, let's just continue on then. So, are the following species isotopes, ions, or different elements? Okay, so isotopes, different mass. Ions involve different charge. And different elements, they have different number of protons. Okay, so if we compare magnesium 2+ and magnesium, what's the main difference? The charge. So these are ions. Or this is a set of a neutral atom and its ion. Okay, oxygen 17 and oxygen 18, would we call these isotopes, ions, or different elements? Isotopes. We have a different mass number, so these are isotopes. Looking at the following two species in isotope notation, where is our number of protons? Where is our atomic number located? Bottom left. So let's highlight that with a different color. Here we go. So looking, do we have a different atomic number, different number of protons? So are these two elements different? Yes. So these are different elements. Perfect. Any other questions on this? Okay, let's keep going. This one's fun. This is a percent abundance problem. An element has two naturally occurring isotopes. Isotope 1 has a mass of 6.01512 AMU and a relative abundance. Now I'm going to use a different color for that. And a relative abundance of 7.59%. Isotope number 2 has a mass of about 7 AMU. And I'm asking first and foremost for the percent abundance of the second isotope. Well, if we add up the percentage of isotope 2 plus the percentage of isotope 1, what should our 2% abundances add up to for a 2-isotope system? 100, exactly. So then we can solve for the percentage of isotope 2. So the percentage of isotope 2 is equal to 100%. Minus the percentage of isotope 1, which is 7.59%. That gives us a percentage of isotope 2 of 92.41%. Just keeping in mind that this 100 is an exact number, so it will not constrain your Sig Figs in calculations. Perfect. So with this in mind, we now have enough information to calculate the atomic mass. So let's do just that. Let's calculate the atomic mass, or average atomic mass of that element. So your atomic mass is equal to the percentage of isotope 1 over 100 times the mass of isotope 1 plus the percentage of isotope 2 over 100 times the mass of isotope 2. Let's now fill in the blanks here. Let's fill in all the information that we know. So the average atomic mass, do we know the percentage of isotope number 1? Do we know the percentage of isotope number 1? What is it? Yep, 7.59. So we have 7.59% divided by 100. Do we know the mass of isotope number 1? Do we know the mass? Yep, so we can plug that in, 6.01512. And this U represents AMUs. Okay, now let's plug in the percent abundance of isotope 2. Did we just calculate that? Yep, so we have 92.41% divided by 100. And do we know the mass of isotope 2? Yes, so let's plug that in, 7.0016, okay? And then just noting that this is an AMU. Let me move this a little bit over to the side to make a little more space to complete this. Okay, so all we have to do now is punch this into our calculator, and that will give us the average atomic mass. So our average atomic mass is equal to, is there a question I can address? Okay, let's punch this in. So we have 7.59 divided by 100 times 6.01512 plus 92.4. Oh, this is where you have to be careful. So you're going to enter this first set in parentheses and the second set in parentheses. So we're going to have 7.59 over 100 times 6.01512. We're then going to hit the addition sign and hit parentheses. Then we're going to do 92.41 divided by 100 times 7.0016. Then you're going to close the parentheses and you're going to hit the addition sign. One moment. And in the end, you should end up with an average atomic mass of 6.92672 AMU. But looking at our component measurements, what is the least number of Sig Figs in this calculation? 3. So we are constrained, and we can report up to, from this first number, 3 Sig Figs. This second number, we can report 4 Sig Figs. Now, just thinking a little bit about decimal place rules for a moment. If we think about the number that we get out of our first calculation, it reported to 3 Sig Figs, it would be 0.457. So this is out of our first calculation. And out of our second calculation, we get 6.470. So if we think about adding these two numbers together, addition is concerned with what? Decimal places. So how many decimal places can we report? 3. So then we can report up to the third decimal place. So our average atomic mass would be 6.92. We look to the right. Do we round up or down? Up. So 6.927 AMU. Just to be 100% precise on reporting Sig Figs. That's not the 100% the purpose of this question. I'm mainly looking to see if you can actually calculate the average atomic mass, but nonetheless, if I'm presenting a solution, I want it to be 100% correct. Does that make sense? Always make sure when you're entering things in a calculator, you write down the numbers from each component step and just check that you're following Sig Fig rules in each step. Okay, any questions on this example, or can we keep going? Yes.
How many points would we lose if we put the incorrect number of Sig Figs?
Probably like 1 on this question. Yeah, small percentage. When I'm asking explicitly for Sig Figs and calculations, or in your lab reports, I'll take off more. But for here, this is more testing your mechanics of calculating average atomic mass. Okay, let's keep going. Let's explain a little bit. Why does the isotope atomic mass not match the atomic mass in the periodic table? So for example, if we're looking at this element, so before we address this question, let's get this elephant in the room out of the way. What average atomic mass corresponds? What element corresponds to this average atomic mass? Lithium, exactly. If you go to your periodic table, we go to our periodic table and we try to find an element with an average atomic mass of close to 6.9, we see the best match would be lithium. So we've been doing a calculation for the average atomic mass of Li, which is lithium. Now, let's get to the meat of this question. Why do the masses of these isotopes, lithium-6 and lithium-7, why do they not match the average atomic mass found in the periodic table for lithium? Yeah, and fundamentally, what is the mass reported in the periodic table for lithium? It's the average, exactly. So this atomic mass here is a weighted average of all isotopes. Of all isotope masses. So by definition, if you're taking a weighted average of all of your isotopes based on their abundance and based on their mass, then obviously the mass of an individual isotope will not match the mass given in the periodic table. That's the real point I wanted you to think about. Just the fact that the mass reported in the periodic table is a weighted average of all isotopes based on their abundance. So you're never going to see a perfect match between an atomic mass and isotope mass by definition, unless there's only one isotope. Does that make sense? Essentially just pointing out to the fact of you've been calculating the average atomic mass. The thing that appears in the periodic table is the average atomic mass. It will never match an individual isotope unless there's only one isotope for that element. Everyone okay on this? Yes.
So can we pick any element or does it be lithium?
Sorry, what do you mean? So this is true for all elements where there's more than one isotope. The average atomic mass, since it's the average of the mass of all isotopes weighted by their abundance, by definition, the mass of an individual isotope will not match the average atomic mass. Does that make sense? Okay. So let's now switch to nomenclature. This is a bit of a review from the previous few lectures. So we're asked to name each of the following. So we're going to put the name on the left-hand side and then the ions and their charge on the right-hand side. So with that rule established, let's look at this first example. So is this an ionic or a covalent compound? Ionic. This is an ionic hydrogen-containing polyatomic ion-based compound. Okay, so first things first, we name our metal, which is cesium. Okay, so we check that off, and then we name our polyatomic ion. So H2PO4. Since we have two hydrogens, what prefix do we use? Di. So this would be dihydrogen. And then PO4, what do we call that? Phosphate. Okay, if we're dissecting this into the component ions, we'd have cesium plus, that follows periodic trends. And then so look, how do we deal with this H2PO4? Is it one entire polyatomic ion or do we break it up into pieces? One entire, it's a hydrogen-containing polyatomic ion. And what's the charge of this polyatomic ion? -1. There we go. Perfect. P2O5. Let me switch pen colors for that because it's slightly different. Is this ionic or covalent? Covalent. So how do we name covalent? We have two phosphorus atoms, so we'd write it as diphosphorus. Yes, diphosphorus. And then we have 5 oxygens. So what prefix would we use? Pent. So this would be pent. And then instead of oxygen, we would change the ending to IDE. So it would be pent oxide. Okay, do I need to put any charges or anything? Does this covalent compound have any charge species in it? No. And that's the entire purpose of this, to not only check that you know how to name compounds, but also that your identification is correct. If I see your name is incorrect and you've also misidentified the compound as ionic when it's in fact covalent, then I get a sense of your thinking in this process. Okay, let's keep going here. So AgClO4. So do we have a transition metal at play? Do we have a transition metal? Yes. Is this silver your typical transition metal? No. What's so special about silver? Fixed charge. Yep. Silver, you'll always just see Ag+. So then we're going to name this just like your typical polyatomic ion containing ionic compound. So we're going to write the name of our cation, which is silver. Do I need to specify the charge for silver? No, it's a fixed charge transition metal. What do we call ClO4? What do we call that? Perchlorate. So this would be silver perchlorate. Okay. And my question to all of you is, in terms of charges, what's the charge of perchlorate? What's the charge of ClO4? -1, exactly. Perfect. Everyone okay so far? Okay, let's keep going now. For CuNO3, let's take a moment and let's identify, is copper a transition metal? Yes. So then, before we do anything, we're going to have to figure out the charges. So in CuNO3, in order to figure out the charge, we reverse cross our subscripts, and that gives us Cu plus and NO3 minus. Does this predicted charge for nitrate match our predictions? Yes. Does it match the preferred charge, the actual charge of nitrate? Yes. So everything checks out. So now that we know the charge of copper, we're going to write the name of our cation, which is copper. And then what do we have to put in parentheses? Because it's a transition metal. The charge, which is 1. And then what do we call NO3? What's the name of that polyatomic ion? Nitrate. So this is copper 1 nitrate. Does that make sense? Again, this number in Roman numerals represents the charge of our polyatomic ion. Everything good so far? Yes. Mhm.
For silver perchlorate, is it necessary to put the Roman numeral 1?
No, you actually do not, because it's a fixed charge transition metal. You only put the Roman numeral if it's not a fixed charge. Yes. So looking, any other questions on this? Yes.
For B,
Yes.
because I put diphosphate, but when it comes to covalent, is it
For covalent compounds, you only write the name of each element. So you write the name of your first element with a prefix, then you write the name of your second element with a prefix, changing the ending to ID.
I think we changed the ID over here, but over here we changed it to O or phosphorus. That's the phos. Never mind.
Oh, this is just the name of the element,
I
phosphorus.
thought it was, never mind.
Yeah. Oh, yeah. I know it's a little bit. I know some phosphorus and phosphorus are often easily mistaken. Don't worry about it. Okay, let's look at H2s Aqueous. Always keeping in mind the state symbols. So aqueous. So how do we name binary acids in the aqueous form? So what do we start us off with? Hydro, yep. So this is hydro. And then S is sulfur. So we change the ending. Instead of sulfur, it would be sulfuric. So this is hydro, sulfuric. And then since it's an acid, what do we write at the end? Acid. And since it's not an ionic compound, we don't have to worry about putting the charges. Does that make sense to everyone? Not too bad, right? Let's keep going now. Yes. So ionic compounds are composed of a metal and a non-metal or a polyatomic ion, while covalent compounds are composed of 2 or more non-metals. Okay. Now let's focus on writing some formulas. This is where things get a little bit interesting. Let's write the formulas for each of the following species. Yes.
So what would happen if we put like the charges for all of them, like regardless of whether
Then I'd mark it off if it's covalent or an acid. So hypobromic acid. So let's take a look. Hypobromic. What Oh, so hypobromic. So this is a typo. This should be hypobromas. I apologize for the typo. I just caught this on the exam. So hypobromous acid. So this is derived from hypobromite. And the hypoite prefix and suffix pair, do we have the most or the least number of oxygen atoms for that polyatomic ion series? Least. So this would be BRO minus. So if we're looking at hypobromous acid, considering we have BRO minus and we want to, we're thinking of an acid, so we're pairing this polyatomic ion with H plus, we cross our subscripts and we end up with a 1-to-1 ratio of HBRO. Does that make sense? The hypoite is the least number of oxygen atoms in that polyatomic ion series. Let's take a look at ionic compound now. Magnesium nitride. So I haven't given you the charges, but can we get them from the periodic table? Yes. So let's talk a little bit about how we generate the charges from the periodic table. So for magnesium, what is magnesium's group number? Yep, so it's a group 2A. So what charge does magnesium adopt? 2 plus. Likewise, nitride is referring to nitrogen, and nitrogen is a 5A element. So what charge will it adopt? Yep, -3. Just as a refresher, the charge is equal to the group number for main group cations, and the charge is equal to the group number -8 for main group anions. So with both of these charges in mind, we can cross our charges and get a valid formula for magnesium nitride, which is Mg3N2. Does that make sense to everyone? If you need a review on charge preferences, I would look at your chapter 3 notes. Okay, let's keep going now. Do we have any questions? Okay, let's keep going then. So ammonium chlorate. So we need to write out the formulas and charges of each of these polyatomics. So ammonium, what is ammonium? Yep, so we have NH4 plus, okay. And what is chlorate? ClO3, and most importantly, what's the charge? -1. So we cross our charges, and that gives us NH4 ClO3. Not too bad, right? Let's continue on. Let's look at a mixture between a compound containing, well, not a mixture, a compound containing a main group metal and a polyatomic ion. So lithium, what is lithium's group number? 1A. So what is the charge of lithium? Plus, okay. Dichromate is what? Cr2O7, and what's the charge of dichromate? 2 minus. Remember, any of the ions in that polyatomic ion table you're potentially responsible for, and they may come up in the chemical reactions chapter. So I'm not just having you memorize these for a random reason. These compounds involving these polyatomic ions are very common in chemical reactions. So now that we know the charges, can we get the formula? Yep, so we take each of our charges and we cross them into our subscripts, and that gives us Li2Cr2O7, or lithium dichromate. Does that make sense to everyone? Okay, let's continue from our more obscure sets of polyatomic ions, but nonetheless, they do pop up. Cobalt-1 permanganate. So this is a transition metal containing ionic compound. How do I know there's a transition metal? Cobalt and the Roman numeral is a dead giveaway. So what's the charge of cobalt? CO. Oh, whoops, one moment. Yep, the charge of cobalt is +1. Permanganate. What's the formula of permanganate? MnO4, and then what's the charge? Minus, yep. Super common in redox titrations. Permanganate ion is a relatively strong oxidizing agent. So let's cross our charges into the subscripts, and that gives us COMnO4. So you really want to brush up on your polyatomic ions, especially the more common ones. All the polyatomic ions in the table, I would expect you to know on the exam. Does that make sense? Now for a little bit more higher order thinking when it comes to writing names and formulas. Do we have any questions on this, or can I move on? Okay, I guess we're free to move on. So we're asked to write the names and formulas of the following compounds. So we have a molecular substance AX, where A is a group 4A, period 2 element. Wonderful. So what is a group 4A, period 2 element? So if we look in our periodic table, if we go all the way to the front of this exam, go all the way to the front, let's find it on our periodic table sheet. Group 4A, period 2. What element is that? Carbon. Exactly, exactly. Perfect. So let's zip back down now that we're comfortable with that kind of triangulation. Okay, so we have a species containing carbon. So A is carbon, and X is a period 3 group 6A element. What element does that correspond to? Sulfur, exactly. Okay, so this would be, since it's a molecular or a covalent compound, we'd call this carbon. And then since we have one sulfur atom, what prefix do we use? Mono. So this would be carbon monosulfide, a relative of carbon monoxide. Does that make sense? The logic behind this? You write out each of your elements, and then in turn, once you have the formula, you use your naming rules. In this case, since it's a molecular or a covalent compound, we use covalent compound naming rules. Let's try another example. We have an ionic compound X2Y3, where X is a transition metal with atomic number 21, and Y is a group 6A, period 2 element. So let's go to our periodic table first, and let's find out atomic number 21. What is that? Scandium. Yep. Okay. Perfect. And now let's zip over, and a group 6A, period 2 element, what does that correspond to? Oxygen. Okay. So filling in the blanks, we have scandium. We have 2 scandiums and 3 oxygens. Okay. Since this is a transition metal containing compound, we're going to need to figure out the charges. So let's reverse cross the charges. That gives us scandium +3, and oxygen is O2 minus. Does this match the projected? Does this match the correct charge for oxide? Yes. So all is right with the world. So we write the name of our cation, which is scandium. And then do we need to specify the charge using a Roman numeral?
Yeah.
Yes. So this would be 3. And then instead of oxygen, we call it oxide. So this is scandium 3 oxide. Does that make sense to everyone? Okay, are we able to continue on with the next few sets of examples? Okay, let's keep going then. So we have an ionic compound containing silver and a group 5A, period 2 element. So silver, that's a dead giveaway. We have silver, okay. A 5A, period 2 element, what is that? Nitrogen, okay. Now let's think about charge preferences here. Let's fill in our charges. What is the preferred charge of silver in ionic compounds? +1, And then nitrogen, given that it's a 5A element, 5 minus 8 gives us a preferred charge of -3. We cross our charges, and then we get, as a result, Ag3N. Now, this is the formula. We've written out our charges. Now let's name this. So let's name our cation first. What's our cation? Silver. Do I need to specify the charge of silver? No? Okay. And then what do we call, instead of nitrogen, it's nitride. So this is silver nitride. Okay, perfect. Let's keep going then. Any other questions?
So there's no Roman numeral for that?
Because is silver variable or fixed charge?
It's a fixed.
Fixed charge. So you don't, fixed charge, you don't have to put the Roman numeral.
Oh, okay, so fixed charge, no Roman numeral.
Yes, exactly. Yes.
Professor, the fixed charges are like
Silver, oh, let me write it on the side. Silver plus, cadmium 2 plus, and zinc, yes. Yep, those are all the fixed charge. Cadmium, let me fix that. CD. So these are fixed charge. Okay, let's keep going with this. Do we have any other questions? Okay. So we're asked, we have an ionic compound containing a period 3 group 7A element and an isoelectronic main group metal cation. So isoelectronic, we discussed this in lecture in passing. What does isoelectronic mean? We have the same number of what? Yep, same number of electrons. Okay, so first things first, a period 3 group 7A element. What element is that? So let's go to our periodic table. Period 3, so we're in the third period, 1, 2, 3. Group 7A, what element does that correspond to? Chlorine, yep. Okay, perfect. We're getting somewhere now. We're getting somewhere. So let's write that down. Okay, so we have chlorine. And what is the preferred charge of chlorine, given that it's a 7A element? Yep, so we have Cl minus. And if we think about Cl minus for a moment, chlorine typically has 35 electrons, 35 electrons, right? But since its charge is -1, if we're calculating the number of electrons, we take our typical number of electrons, which is our atomic number, and then we subtract our charge, which is -1. So this chloride has 36 electrons to its name. So our goal is to figure out and find a metal cation with 36 electrons. So let's go to our periodic table. And a quick trick to figure out isoelectronic species. Oh, sorry about that. Let me correct that. Chlorine typically has 17, so we need 18. I keep thinking about bromine for some reason when we keep talking about this. I keep thinking about bromine whenever we talk about chlorine. Okay, so the quick trick to identify isoelectronic species. So you put a box around your element, right? Okay, everyone done that so far? Now, what you're going to do is you're going to draw an arrow and count how many spaces it takes to reach a noble gas. So 1. So just 1 space over, right? Now, if you want to figure out an isoelectronic cation, what you do is you box in elements after the noble gas and you count the number of spaces needed to reach the noble gas. So in this case, potassium would take 1. So if you're isoelectronic with Cl minus, we need to have potassium plus. The negative charge is equal to the spaces moved to the right. The positive charge is equal to the spaces moved to the left. Is there another ion that's isoelectronic with chloride? by this rule? Is there another element that we can get all the way to argon from? Would calcium also work? Yes, but let's be specific. It takes how many spaces? 2. So we need calcium 2+. Would scandium also work? Yes, it would just be scandium +3. Would titanium work? How many spaces? 4. So it would be titanium +4. Does that make sense to everyone? So this is the rule for figuring out isoelectronic species. You essentially count the number of spaces you need to reach the noble gas, and then that is the charge of the isoelectronic cation. Let's showcase the more classical way of doing it, just using the tools that we currently have. If I want to figure out a cation with 18 electrons, well, I'm going to write out a list of prospective cations. So I know potassium typically has 19 electrons to its name. So if I want 18 electrons, what charge does potassium need to adopt? +1, exactly. And is potassium plus a common form of potassium ions? Does potassium like to adopt a +1 charge? Yes. So even using just our simple isotope notation method, we can count the number of electrons in both our cation and anion and see the number of electrons is same or different. Do we have 18 in the end?
Yes.
Yes. So do we have the same number of electrons? Are they isoelectronic ions? Yes, exactly. And now once you have that established, we can definitely write the formula of something containing potassium and chloride ions. It's just KCl. A lot of work for a really simple formula. Now, what do we call KCl? Now, what do we call KCl? Potassium. And then instead of chlorine, we call this chloride. Perfect. And that's it. Does that logic make sense to everyone? Worst case, write out your prospective cations, count the number of electrons, and if it has the same number of electrons as your anion, they are isoelectronic. Same number of electrons. Does that make sense? Everyone looks tired right now. Don't be shy to ask questions. This is mostly for you. Okay, now let's move on to the law of multiple proportions and the laws associated with chemical composition. So I'm going to write out and transcribe this word problem into some useful form. So when 8 grams of carbon is reacted with 2.66 grams of hydrogen, 10.66 grams of carbon tetrahydride or methane is formed. So we have 8 grams of carbon plus 2.66 grams of hydrogen, and we end up with 10.66 grams of CH4. So I'm asking you, what is the formula of a compound formed by reacting 16 grams of carbon with 2.66 grams of hydrogen? So we have 16 grams of carbon plus 2.66 grams of hydrogen. And my question is, what is the formula? CXHY. Well, using the law of multiple proportions, the first thing we need to establish is what element mass does not change in these two reaction problems. Hydrogen, right? So if the mass of hydrogen used in both of these reaction studies does not change, will we end up with the same number of hydrogen atoms incorporated in our molecular formula? Yes. So then we know we have already established that there are 4 hydrogens in our chemical formula. Perfect. Let's now look at our variable element, the element where the mass changes between experiments. So we know in the first experiment that we have how many atoms of carbon in our product? In CH4? 1. So we have 1 carbon atom per every how many grams of carbon that we subjected to a reaction? 8 grams, right? Does everyone notice the relationship? We're just reading off from this problem, right? The atoms of carbon from the formula, the mass of carbon from the problem description.
We get the atoms from the product.
Yes, exactly.
And we get it from the
Now, yep, you always get it from the product. Since you're relating the atoms of carbon in your product to the mass of carbon that you reacted. So now we know in our second problem, we used how many grams of carbon? 16. So then that in turn cancels out and we get 2 carbon atoms. So then we'd predict a formula of C2H4. Although technically this method is only capable of giving you the empirical formula, so it's certainly accept if you wrote CH2 as an answer. Technically this compound is C2H4 because CH2 is not actually a valid it's not actually a valid formula for an isolable species, but we don't have those rules yet to be able to definitively say. So if you put C2H4 or CH2, I'd give you equal amounts of let me check on this. I would be able to give you credit for both equally because this method is only able to give you empirical formulas. It's only able to give you the simplest ratio of atoms of each element. Does that make sense to everyone? Okay, let's take a look at another example of the law of multiple proportions, this time applied to composition. So copper and chlorine form many different compounds, including copper 2 chloride. Decomposition of a sample of copper 2 chloride produced 25.83 grams of copper and 28.36 grams of chlorine. While decomposition of an unknown compound of the formula CuClX produced 25.83 grams of copper and 14.18 grams of chlorine. Okay, so this is another law of multiple proportions problem, this time applied to composition. So let's start with part A. We have to calculate the mass of chlorine per gram of copper for the sample of copper 2 chloride. Well, it seems to me like we already have all of the information we need. So all I need to do is find my mass of chlorine. What's my mass of chlorine? Yep, 28.36 grams of chlorine. And this time I'm using single, well, it's technically chloride, but I'm using the atomic form because we're referring to elemental composition. So these are the atoms, this is the mass of chlorine atoms in my sample. Okay, and what mass of copper do we have? Yep, 25.38 grams of copper. So punching that into our calculator. That gives us 1.1174 grams of chlorine per gram of copper. We round to 4 Sig Figs. So is 4 greater than or less than 5? Less than. So that gives us 1.117 grams of chlorine per gram of copper. Okay, now we're going to repeat the same process for our unknown sample. So we're going to calculate the mass of chlorine per gram of copper for the unknown sample. So how many grams of chlorine are in our unknown sample? How many? How many grams of chlorine are in our unknown sample? 14.18. So we have 14.18 grams of chlorine. And how many grams of copper do we have?
25.38.
Yep, 25.38 grams of copper. So we just punch that into our calculator, 14.18 divided by 25.38, and that gives us 0.5587 0 grams of chlorine per gram of copper. We round it to 4 Sig Figs, and that gives us 0.5587 grams of chlorine per gram of copper. Does that make sense to everyone? Okay. Now we're really into the meat of this problem, and the reason why I had you write this out is we can very quickly identify our fixed mass and our variable mass elements. So let's highlight what's going on in this problem. So in our first case, we have 28.36 grams of chlorine and 25.38 grams of copper, and this corresponds to a formula of CuCl2, or copper 2 chloride. Does that make sense? So now, we know that we have how many atoms of chlorine? How many atoms of chlorine do we have? 2. So we have 2 chlorine atoms per how many grams of chlorine? For how many grams of chlorine? 28.36. Now, if we compare our two experiments, does the mass of copper, and as a result, do the atoms of copper change? No, right? The mass of copper isn't changing, so the atoms of copper in our formula is not going to change, right? So then, since the only thing that's changing is the mass of chlorine, in our second experiment, how many grams of chlorine did we have in our sample? 14.18, right? So if we want to figure out the atoms of chlorine in our unknown sample, we just multiply this ratio by the mass of chlorine. And that in turn gives us, we have 2 over 28.36 times 14.18. And that in turn gives us 1 chlorine atom. So then, if our mass of copper is the same, should we have the same number of copper atoms in our formula? Yes, right? So we'd write this as Cu, and then how many chlorine atoms did we calculate? 1, so it would be CuCl. Does that logic make sense to everyone? If it's fixed mass, then we have the same number of atoms in our formula in each of the 2 compounds. For variable mass, we write a ratio between the atoms of an element and the mass of that element that reacted. We then multiply by the mass of element used in our second experiment, and that gives us the atoms incorporated into our product in our second experiment, in our second compound. Does that make sense? So this is a precursor to stoichiometry and other percent composition calculations that we'll be doing in chapter 4. So let's now name the unknown compound. So CuCl. So figuring out that copper, what's so special about copper? What's something that we need to look out for copper? Transition metal. So what do we need to figure out? The charge. So let's reverse cross the subscripts to the charge, and that gives us Cu plus and Cl minus. So now we have some information to name this compound. So this would be copper. What's the charge of copper? 1. And then instead of chlorine, we'd write chloride. Okay, perfect. All set? Does that make sense to everyone? Okay, let's now continue on. So this is now a classic practical experiment where you're asked to take some measurements on a sample graduated device. So the after picture you'll see later on in this problem. Let's focus on our before picture. Let's focus on this before picture here. So First and foremost, when you're taking a measurement using a graduated device, you're going to need to be able to figure out the value of a tick mark. So from 9 milliliters to 10 milliliters, it takes us how many ticks? 10. So 1 mil is equal to 10 ticks. So then 1 tick is equal to 1/10 of a mil, which is 0.1 milliliters. And then finally, 1/10 of a tick is equal to 0.1 divided by 10, which gives us 0.01 milliliters. Does that make sense so far? So what place can we report up to? Tenths or hundredths? Hundredths, exactly. Next, when you're measuring volumes in, keep in mind, do we measure from the top or the bottom of the meniscus? Bottom. Okay, so we're at the 1, 2, 3, we're at the, a little bit, we're almost right at the 4th graduated mark. So what would we write that as? 9.40 mils. 9.41 is also fine, as long as you're within 1 unit of the estimated digit, which is your hundredths place. Okay, let's go with 9.40 to make the math a little bit nicer. Okay, so we have our initial volume as 9.40 milliliters. Okay, let's now take a moment. The empty beaker containing the sample was weighed, and the mass of the empty beaker was found to be 5.35 grams. So 5.35 grams is equal to the mass of your beaker. Okay, the solid was added, and the final mass was found to be 15.72. So the mass of the beaker plus the solid is equal to 15.72 grams. So then, can we figure out the mass of the solid by difference? Yes, this is classic weighing by difference. So we take 15.72 grams minus 5.35 grams. And that in turn gives us, yep, exactly right. So we have 10.37 grams. Again, remembering that you're retaining 2 decimal places in this case. Since subtraction, we care about what? Subtraction, we care about decimal places. Exactly. Okay, perfect. So we have the mass of the solid. We're good to go. We're just blazing through these questions. So the metal sample was suspected to be copper. So determine the expected volume of the solid metal sample given the following table. Okay, so we know that volume is equal to mass over density, right? Right? So if we suspected our sample to be copper, can we look up the density? Yeah, so the density is in gram per mil. I should have specified that. I apologize in advance for that. So we know that our mass is 10.37 grams. So do we have both pieces of information needed to calculate the volume? Yes. So we have 10.37 grams divided by 8.9 gram per milliliter. And that gives us an expected volume of 1.165 milliliters. How many Sig Figs do we have to round to? 2. So we take our 1, we look to the right. 6 is greater than 5, so do we round up? Yes. So we get 1.2 milliliters. So we'd expect a displacement of 1.2 milliliters for this sample. Does that make sense? Okay. Any questions so far? Does it make sense how we're using this data table? All we're using it is to read off the density. Does that make sense? So did we calculate the mass of our sample previously?
That's where we get it from.
Yep, exactly.
Okay.
Yep, so we calculated in step B, and step C is saying we have this sample, we know its mass. Can we predict its expected volume given the density? Does that make sense? Perfect. So if it's a sequential question like A, B, C, D, and E, make sure you refer to the previous steps. Okay, let's keep going now. What is in store for us here? So the volume after the addition of the solid is shown below. So from this information, we're going to determine the identity of the unknown metal. Wow, that seems like, how do we get that from this? Well, we've established previously our volume initial all the way at the beginning of this problem. What was our initial volume here? 9.40. We've done this in lab. We record our initial volume. Now, all we have to do is record our final volume. And thankfully, since we're using the same graduated instrument, we have to be using the same graduated cylinder for the displacement method. What is our final volume reading about? We're past the second mark, so it's about 10.25. Sure, that's fine. You can also say 10.24 milliliters. 10.26 milliliters, as long as you're reporting to the hundredths place for this specific instrument. Perfect, perfect. So then we can know, and can we calculate the volume of our solid by difference? Yes, so the volume of our solid is volume final minus volume initial. So the volume of our solid is equal to 10.25 milliliters minus 9.40 milliliters. So we have 10.25 minus 9.40, and that gives us 0.85 milliliters. So that's the volume of our solid. Does that make sense to everyone? Yes.
0.884 milliliters be acceptable too?
Yes, yes, yes. Depending on what your initial and final volumes are, you'll get a slightly different number. But all the correct responses will have how many decimal places? 2. So just make sure you're following that. Now, given that we have the volume, if density is equal to mass over volume. Now, to address the question, why are we calculating density? Do we have this giant table? Do we have this table that tells us the exact element identity as a function of density? Yes. So then, would we want to calculate density to assign the element identity? Yeah. Okay. So let's do just that. So if density is mass over volume, we plug in our mass of 10.37 grams. Do we know our volume? Yep, 0.85 milliliters. So that in turn gives us 10.37 divided by 0.85. That gives us a density of 12.2 gram per milliliter that we have to round to 2 Sig Figs. So that gives us just 12 gram per mil. Now our goal is, given this information, let's go to the table and try to find our best fit. Our best fit for this 12 gram per mil density. Does it make sense how we calculated this density? Yes. Okay. Well, this is exactly identical to a lab that you've done this semester. Does everyone remember that lab? I remember. Where you're measuring the density of variable solid cylinders? I remember. Yeah. So nothing is something you haven't seen before. Okay, so if we have a density of about 12 gram per mil, what element best fits this very, very dense block? Lead. Yep, lead has the largest density that's closest to 12, so we'd assign this unknown metal block to be a block of lead. Does that make sense? Okay, so we'd assign this to be PB, which is lead. Okay, any questions on this example? It's exactly the same analysis that you did for lab. So This is just a forewarning. I like to write questions for exams based on labs. Let's now complete the following last set. We have to carry out the following mathematical operations. In this case, we care a lot about Sig Figs. So in this first case, we have a subtraction operation followed by multiplication. So we have 3.0 minus 0.45. Okay, in subtraction, what do we care about? Decimal places. This first number has 1. The second number has 2. 3.0 minus 0.45. So how many decimal places should we retain? 1. So we get 2.55. We're going to use bar notation here. To note the fact, we're going to use bar notation over the first decimal place to note that is the last reported significant digit. Next, we're going to do multiplication. So if we have 2.55 multiplied by 2.0, how many Sig Figs does this 2.55 actually have if we're reading bar notation? 2. And how many Sig Figs does 2.0 have? 2. Okay, so if we punch that out, we get out 5.1. Make sure not to round until the end of your calculations. Finally, let's do one last. We have 2 more to do, actually. The next one, we're doing a percent error calculation. So first, we're taking 1.35 minus 1.34567. Sure. So since we're dealing with subtraction in the first case, how many decimal places do we need to care about? How many decimal places do we retain? 2. The first number has 2, second number has 5. We retain 2 decimal places. 1.35 minus 1.35 minus 1.34567. That in turn gives us 0.00. This 0 is the last reported significant digit, but we'll retain these other digits to complete our calculation. Okay, next we have 0.00433 divided by 1.34567. Okay, now looking at this top number, it may get a little bit tricky when you're thinking about how to deal with bar notation for these types of numbers. So the best way to help deal with this bar notation and to help get a sense of the number of decimal places and the number of sig figs that you'll need to retain is to just consider looking at these first 2 numbers. So if they were not zeros, we're considering those significant decimal places, right? We want to retain 2 significant decimal places, right? So how many sig figs, how many significant digits are we currently indicating using this bar notation? 2. Yeah, so this has 2 sig figs. And this bottom number has 1, 2, 3, 4, 5, 6 sig figs. So overall, our output number will have 2 sig figs in total. So we divide by 1.34567, multiply by 100, and in turn, at the end of this, we'll get 0.3217. If we need to round to 2 sig figs, we look to the right. Do we round up or down? Down. That gives us 0.32%. Now, for those asking, why doesn't this 100 cause problems? What type of number is this 100? Exact. So its numbers as part of formulas, conversion factors are considered exact. Same as numbers derived from counting. Does that make sense to everyone? Okay, let's keep going now. Ethanol has a density of 0.8 gram per milliliter, and I'm asking the mass in kilograms of 0.2 centiliters of ethanol. So we're starting with centiliters of ethanol, and at the end of this, we want to end up in kilograms. So looking at our density, what are the units of density? What are the units? Gram per mil. So in order to use our density, as a conversion factor, what units does our volume need to be in? Milliliters. So we need to go from centiliters to milliliters. And then from milliliters, what units does our density allow us to go to? Grams, exactly. So this is our full unit solution map. And from this unit solution map, just like any other unit conversion, we can now execute. This is the idea of unit analysis. So we have 0.2 centiliters. And my question is, how many liters do we have in 1 centiliter? Yep, 10 to the negative second. To go from liter to milliliters, what goes on top? Mils or liters? What goes on top? What are we going to? Milliliters. So in 1 milliliter, we have how many liters? Yep, 10 to the negative third. And to go from milliliters to grams, what needs to be on top? What? Sorry, to go from milliliters to grams, what needs to be on top? Grams. So we need to have something in the form of gram per mil. Do we have that for ethanol? Do we have the density of ethanol? Yes. So how many grams are there per 1 mil? 0.8. And let's be specific here, it's 0.80 grams. And then to get to kilograms, what goes on top? Kilograms. So we have 1 kilogram per how many gram? 10 to the third, exactly. So now all we have to do is punch this into our calculator. Now looking at Sig Figs, how many Sig Figs do we report? 1. This centiliter has only 1 Sig Fig, so then we report an answer with 1 Sig Fig. So we take 0.2 times 1 EE negative 2 divided by 1 EE negative 3 times 0.8 divided by 1 EE3. And that in turn gives us 0.0016 kilograms that we in turn round to 0.002 kilograms, or 2 times 10 to the negative third kilograms. There we go. So this is an example of integrating unit conversions with density calculations. Any other questions on this? Any other questions on the exam? Yes.
So I can leave it at 0.002, right?
Yes, that's perfectly fine. It's perfectly fine because it has the correct number of Sig Figs. Yeah. Yes. All set? So as you see, even when we're going through it slowly, we still have 30 minutes to spare if we were working on this exam together. So focus on studying and preparing for your exam. Try working on the pre-lecture quizzes. And remember, please bring your calculator. Please bring a writing implement. The last thing you want is to have your exam jeopardized by not having all the tools at your disposal.